Hello everyone. I hope that you are enjoying watching these lectures on structure of atoms chapter, okay, of class 9th. Okay. So, this is the whole series of lectures in which we already completed lecture 1, lecture 2, lecture 3, and lecture 4. Okay. Now, this is lecture 5 of this whole series, in which we are going to learn few very important things about Bohr's model of an atom. Okay. We already have completed learning about Thomson's model of atom and then Rutherford's model of atom. Okay, now we are ready to learn the Bohr's model of an atom. Okay, so the Bohr's model of atom was very similar to that of Rutherford model. Okay, but there was some very, you can say, important changes he made. Okay, he proposed. We will discuss those. Okay, and then the application of Bohr's theory, and then Bohr-Bury rule, in which the arrangement of electron in an atom, what he proposed. Okay, so let's start with this Bohr's model of an atom. Okay, yes, I was saying that Bohr's model of an atom was very similar to, very identical to Rutherford's model. But like Rutherford was unable to explain that how these electrons are revolving in the orbits around the nucleus. So then, like, Maxwell's theory was there that when electron is moving in a circular path, so then it will have some acceleration associated with it, and due to that acceleration, electrons are going to lose energy, and then ultimately they are going to fall into the nucleus. Okay, so this was all like the you can say that this was the drawback of Rutherford's model. Okay, so then Bohr came up with an idea, an idea that he proposed, that yes, it is correct that when electrons are going to revolve in orbits around the nucleus, then they are going to experience some acceleration, and that's how they are going to lose some energy, and then ultimately, eventually, they are going to fall into the nucleus. But he said he said that it will happen, but when the electrons are going to revolve around the nucleus in some specific energy orbits, okay, so then this is not going to happen. He proposed that if electrons are revolving in these orbits, they will have some energy. Okay, they will have some very specific energy. So, and he named these orbits as stationary orbits or energy levels. Stationary orbits or energy levels. So he proposed that when electrons are revolving, is present in stationary orbit, then it is not going to fall into the nucleus. These are stationary orbits. It means that if electron is present in the stationary orbit or energy levels, then it will have a, you can say, stable arrangement. Clear? Now, one more thing. There are many things like this. So this was nucleus. All the positive charge is centered here. Okay, and electrons carrying individual negative charges are revolving around this nucleus. And see, the name energy level means what? Means that if the you can say the first orbit, which is just outside the nucleus, will be called as first orbit. So either we can say n is equal to 1 or k shell. Okay, so k shell or k energy level, or n is equal to 1. Then next is n is equal to 2. So all these this will be called L. Okay, like this m and then n and then like this. Okay, now energy levels means what? It means that n is equal to 1 will have lower energy and n is equal to 2 will have higher energy. It means the electron which is present in this n is equal to 1 will have lower energy as compared to the electron which is okay present in the outer shell. Okay, so it means that, so as they are arranged in increasing order of their energies. Okay, now so these are the few things about Bohr's model of the atom. And he also explained that no what are these orbits, how is these orbits are going to like have a stable configuration. So he proposed that since there is like you can say uh, there is quantization, there's one thing called quantization. This is a very important term, from this only quantum theory and all these theories came up. So this quantum theory, everybody wants to know more about quantum theory, and everybody like just quantum theory is like the something which is very fascinating thing about we all about science, and we all want to know more about quantum theory. So this quantum theory actually came from quantization. Quantization is a term, if let's say if I can explain this to you, quantization is means like if you let's say we like one packet of cookies, let's say, and it has we can say 8 cookies, so it is a like packet of one, okay, one very famous cookies, let's say. Okay, and then it has 8 cookies in this packet. Okay, now if we go to a shopkeeper, okay, and we'll ask for let's say 5 cookies only. Okay, so we are not going to get any 5 cookies now. It is like we are going to either have 8 cookies or 16 or 24 or 32 like this only or not. Okay, because see, this will be a packet of cookies. So either you will have, you can buy 1 packet or 2 packet or 3 packet like this only. So 1 packet means 8 cookies, 2 packets means 16 cookies, and then 3, 4 like this only. We cannot have 5 cookies. Are you getting my point? So we can say that it is, we can say that then either we can get 8 or 16 or 24 or 8. In general we can write 8 n cookies or not. Like we keep on changing the value of n, and we will be getting different values of cookies. We will, okay, we can get, are you getting my point? So this thing is called quantization. This thing is called quantization. I hope that you all understood this. So he said that he proposed that when this uh, angular momentum angular momentum angular momentum is something, okay, so we know momentum means m into v, we know. Angular momentum means m into v into r. Okay, simple. So it means that linear momentum, this is called linear momentum. Okay, linear momentum into the radius, so like this. Okay, and then like this. Okay, so he proposed that when angular momentum will have quantized values, okay, quantized values means like n times of the first and then n times, okay, like first angular momentum is mvr, so the second will be like n mvr like this. Okay, so the radius will be n times, okay, like this we can say. Now, so he proposed that the electrons will revolve in the orbit for which the angular momentum is quantized. Okay, this was Bohr's proposal. Let's watch this video to understand it better. So let's watch this video. Okay, so this was the video in which, as I explained, that the Bohr's model has different energy levels. Okay, and the electrons, if you like provide some energy, okay, let's say heat, so then this electron is going to jump to the next higher energy level. Okay, and if an electron is coming back to its original energy level, then it is going to release some energy. So it's like energy, these orbits will have fixed energies, and electrons will be jumping from one orbit to other orbit if energy exchange happens. Okay, now so then we already have done this Bohr's model of an atom. Application of Bohr's theory. Okay, what are the applications? We can say that we already have seen that uh, these electrons will have, can say, particular energy, okay, when it revolves in one particular shell. Okay, now application of Bohr's theory. So application of Bohr's atomic model is like derivation of radius of an orbit of an atom. We can derive the radius of these orbits, okay, by Bohr's theory, Bohr's atomic model. Next is we can derive the energy of these orbits. Okay, we can determine that if electron is revolving in this first orbits, then it will have this much of energy. Okay, and if electron is revolving in the next orbit, then it will have this much of energy. Okay, we can derive these. Okay, even we can derive the wave number, the number of waves these electrons are forming, okay, when they are like revolving in these orbits. So these are the applications of Bohr's theory. Okay, now next is this rule, okay, which by which we will be able to predict the arrangement of electron in an atom. Okay, the distribution of electrons in different orbits or shells is governed by a scheme known as Bohr-Bury scheme. The arrangement of electrons in various energy levels of an atom is known as electronic configuration. It means that how these electrons are distributed, okay, in the atom. Okay, this we will call as electronic configuration. Electronic configuration. Okay, so in this electronic configuration, let's see. According to this scheme, the third shell onwards, the shell becomes bigger. Exactly. Okay, as we move away from the nucleus, the shell becomes, the radius of the shell becomes larger and larger. Now, according to this rule, the maximum number of electrons which any shell can have is 2n square. Okay, so we can write maximum number of electrons in nth shell will be equal to 2n square. Okay, so it means that if we have, let's say, for k shell n is equal to 1 or not. Okay, so we can write it like this. Just wait. N is equal to 1. Okay, so then maximum electrons, okay, will be equal to 2 into 1 square. It means 2 or not. Okay, for L shell we'll have n is equal to 2, so it means 2 into 2 square, it means 8 electrons. Okay, for M shell we'll have n is equal to 3, so 2 into 3 square, it means how much? 18 electrons. Okay, and if for n we'll have 4, so 2 into 4 square, that is 32 electrons. Okay, so like this, 2 electrons and then 8 electrons. In next we can have 18 electrons and then 32 electrons. This is Bohr-Bury rule. Okay, now after this, so if let's say we have one atom in which we have like let's say for carbon atom, so for carbon atom we'll have 6 electrons. Okay, so we'll have a nucleus. Okay, and then in first shell we'll have how many electrons? 2 electrons, because in first shell we can have only maximum 2 electrons. Okay, and then in next shell how many electrons will be there? So out of 6 electrons, 2 are already arranged, and then next 4 electrons will be there present in the next shell. Okay, because the next shell can have 8 electrons maximum. Okay, only 4. So there's still like 4 electrons can come and occupy these their places in second shell. Okay, so this is n is equal to 2 shell and this is n is equal to 1 shell. Okay, like this. I hope that you all are getting these things. Now next, so then now question, define valency by taking example of silicon and oxygen. So like in oxygen, so we'll take these valency thing in next class. Okay, next lecture. In the atoms of oxygen, the valency, okay, yeah, so this was all. I think we can take the previous lectures question here. Okay, related to Bohr's theory. Just wait. We had this question. Describe Bohr's model of the atom. So now we can describe, see, according to Bohr's model of the atom has nucleus at the center. Okay, second, these electrons revolve around the nucleus. Third, certain special orbits known as discrete orbits of electrons are allowed inside the atom. Okay, so the electrons are going to revolve around the nucleus in these discrete orbits, also called stationary orbits or energy levels. While revolving in discrete orbits, the electron do not radiate energy. Electron is not going to radiate energy as it was happening in Rutherford's model when the electrons are in these specific energy orbits. Okay, these orbits or shells are called energy levels, and these orbits or shells are represented by the letters K, L, M, and N, and so on. Okay, and are the numbers with n is equal to 1, 2, 3, 4, like this. Okay, so this was all about this question, and I hope that you enjoyed watching this lecture and also understood all the uh, facts I explained here, everything. What are the applications, what is this rule, what are the maximum number of electrons. Okay, so if you have, like, we will deal with these valencies. So like valency, let me explain this valency to you. Okay, now here, so like this carbon, so carbon have like 4 electrons in its outermost shell or not? Outermost shell, this one is outermost shell or not? So it has 4 electrons. It can occupy 4 more electrons or not? It can occupy 4 more electrons. Okay, okay, and it can also lose these 4 electrons if required. Okay, it can also lose these 4 electrons, or it can occupy 4 more electrons. So the carbon's valency will be 4. The valency of carbon will be 4. Okay, let's take another example of oxygen. Oxygen has 8 electrons, so we'll have nucleus and then 2 electrons, and then in next orbit we will have how many electrons? 6 electrons. So 1 electron, 2 electron, 3 electrons, 4 electron, 5 electron, and then 6 electron. Now oxygen can take 2 electrons more to have 8 electrons in its outermost orbit or not? Okay, so then its valency will be 2. 2 will be its valency. Carbon has its valency as 4. Okay, so it means that either which these atoms can, the number of electrons that these atoms can lose, okay, to form a bond, or the number of electrons which they can take to complete their outermost fully filled orbits. Okay, so that's why we can say that these are valencies of carbon and oxygen. Now we can answer the question, define valency, by taking examples of silicon and oxygen. So like the electronic configuration of oxygen is 2 and 6, and electronic configuration of silicon is 2, 8, 4. So what will be the electronic this valency of oxygen? 2, because it can take 2 electrons to have full house 8. Okay, and electron configuration of silicon is 2, 8, 4, so it can lose these 4 electrons, so its valency will be 4. Okay, yeah, valency of silicon is 4 and valency of oxygen is 2. So I hope that you understood this everything what I explained here in this lecture. So if you have any queries, any doubts, okay, you can post it on forum. We'll be answering them all. Okay, we'll be like interacting with you all. Okay, and keep learning. Okay, thank you for your time. Keep learning from Ask IITians. Okay, and we'll be continuing this chapter in the next lecture. Thank you.